All right, so the next chapter in the Klein textbook's all about ethers. In general, for the rest of the year, I'm just going to ask you to review a lot of the nomenclature or the naming at home. So if you want to, it's section, 14.2 in the first or second edition. That'll cover naming, or if you have the third edition, they changed the chapter order just to make things fun. That's the third edition. So you can read through that. Otherwise, there's a little link on here for the Khan Academy video that covers basic ether nomenclature, but it's pretty straightforward. I did want to go over a few of the common ethers. All right, so there are a handful of really common ethers that we run into in organic chemistry. This is a really common one. Does anybody know what this one's called? Diethyl ether. Kind of looks like a little bat. If you want to do the fancy IUPAC name, you follow a really similar procedure to naming any sort of organic molecule, and that's where you identify the longest carbon-containing functional group. So for example, we could say, well, this is 2 carbons long, and then we've got this substituent coming off carbon number 1. This would be called an ethoxy group rather than just an ethyl group. So you could call this ethoxy ethane. However, most people just simply call it diethyl ether. It's a lot easier. So there's these 2 different naming systems you can use. With symmetric or simple ethers, you can just call it whichever alkyl groups are coming off each side in alphabetical order, followed by ether. However, with more complicated ones, you normally do the IUPAC naming system. All right, there's also another one that's really common. This is one we've actually seen a handful of times. This is THF. Does anybody remember what THF stands for? Tetrahydrofuran. And the reason it's called this is there's an aromatic molecule that looks really, really similar. I'm going to draw it down here. You don't have to. But it looks like this. This is called furan. This is called tetrahydrofuran because basically it's the exact same molecule with 4 hydrogens added in, right? So it's kind of an offshoot of the aromatic molecule's name. All right, there's also one other common one, closely related to THF. This is called 1,4-dioxane. And it's really similar to THF. It's a common solvent. The only benefit to using 1,4-dioxane over THF is it has a much, much higher boiling point. So if you need to really crank up the heat, you can switch to 1,4-dioxane. Essentially, all of these are common solvents, but we have increasing boiling points as we go this way. So if you need something where you don't have to heat it very hot, you can use diethyl ether, but if you need to heat it really, really hot, you'll typically use 1,4-dioxane as your solvent. All right, that leads us to the common uses of ethers. The first one I've already mentioned is it's a common solvent. It's nice to use diethyl ether because it evaporates so quickly and it's cheap. It's also a weak Lewis base. And why do you think that is? What is a Lewis base, first of all? It's an electron donator. So if we go back up and we look at these, all of the oxygens have lone pairs that can be donated. That's why, for example, you see THF paired with borane, BH3, because it'll form this Lewis acid-base adduct with borane and help stabilize it. So it's useful in coordination chemistry. All right, it's also fairly inert, which is good for a reaction solvent, right? You don't want your solvent usually to participate in the reaction. You want it just to kind of act as a reaction medium. And then it can participate in H bonding. Specifically, it's a decent H bond acceptor. And that's simply because it has these lone pairs hanging out that can participate in that H bonding. So really, The most common situation that you'll see ether used is as a solvent. However, once in a while, you'll see them used in functional groups as well. It just depends on the situation. All right. There is another type of ether that's pretty common that we've seen already, and I've got this picture that I'll explain in a second. These are epoxides. And I found this on a guy's blog, I think it was Master Organic Chemistry, and he calls them the black sheep of the ether family. And the question is, well, why is an epoxide, which is this three-membered ring with an oxygen in it, the black sheep of the ether family? Does anybody know? Because it's different, right? So just like this kid doesn't really fit in with the family, why is it different? What's that? It's taking the attention, sure, but why is it so much different than like diethyl ether, for example? Yeah, it's super unstable, right? Each of the carbons in an epoxide are sp3 hybridized. sp3 hybridized carbons prefer to have what bond angle? About 109.5, give or take. In this case, we're forcing it into a 60-degree bond angle. That's incredibly unstable. So let's make a note of that. They are very reactive due to ring strain. All right, now my question for you is, let's say we've got ethylene. That's our basic hydrocarbon building block. What reagent do we need in order to make the epoxide shown? MCPBA, that's one common route. So oftentimes we use peroxy acids like MCPBA to make these. This is also a really useful building block, this compound on the right. So this compound on the right is called ethylene oxide. I think it's 2 words. Or what you may often see it written out as is oxirane. Whoops. Both are acceptable naming systems. However, most of the time when you see that building block, it's ethylene oxide. It's actually used to sterilize surgical equipment. It's used as rocket fuel. It's really energetically powerful stuff due to that ring strain. It's also useful as an organic precursor for building up more complicated functional groups, as we'll see in this chapter. All right, there's other less common ones. One is pretty similar to epoxides, but it's got 3 carbons. These are called oxetanes. Whoops. These are a lot less reactive than epoxides because now we've adjusted the angle from 60 degrees to about 90 degrees. And then we've got ones that are like THF. The parent subclass for THF are called oxalanes. And you can keep on going bigger and bigger and bigger. Honestly, I'm not super interested in you memorizing all of these names. The main one that we're going to be looking at in this chapter are epoxides. Epoxides are incredibly versatile organic building blocks. All right, so now we're going to take a step back and we're actually going to go to these common ethers, these really simple ones, and see how they're made commercially. There's a handful of ways to make these. For really simple ones, you can do this industrial method. And this really only works for simple ethers, meaning you're making something small that only contains an ether functional group, no other functional groups. All right, so in order to do this, you can actually take small alcohols like ethanol. You can treat it with catalytic acid. What do you think the first step's going to be? Protonation. Hopefully everybody's got that one figured out. All right, the good thing is by protonating it, just like we saw before, that this is a bad leaving group. All of a sudden, we've made this into a good leaving group. So this can actually do SN2 chemistry. So let's say we've got another equivalent of our ethanol floating around. This ethanol, as a nucleophile, can actually hit the backside of that ether, kick off our good leaving group. And we end up with a protonated ether. However, we kicked off water as our leaving group. So this water can reach back, steal a proton. We can make something like diethyl ether, and we create our water byproduct. In this case, it's going to be the hydronium ion. So this really only works well with simple ethers. Does anybody know why? What happens if you have an alkene or something in your starting material?
You're going to get a huge mix of products.
Yeah, you get a mix of products. In particular, you'd have to worry about addition reactions, things like that. So really, you can't do this sort of chemistry if you have any sort of acid-sensitive functional groups. So if you've got an alkene, something like that in your starting material, you really can't do this anymore. All right, that leads us to the more elegant synthesis. This is kind of one of my friends called it a shake and bake method. You just kind of shake it up with a lot of acid and heat, and you get out this simple ether. If you want to do it the more elegant way, you have to do something called the Williamson ether synthesis. And the Williamson ether synthesis is something we should all know already. It's basically just SN2. All right, so let's say we've got an alcohol like ethanol. I'm just going to pick on ethanol for right now. This is a pretty crummy nucleophile, right? Nucleophiles are really good if they have a negative charge and they're unstable. How can we make this less stable? We could deprotonate it, right? So we can make an alkoxide anion. So maybe we'll just throw in elemental sodium. We saw that last chapter. And if we do this, we can actually form the alkoxide anion. The countercation is sodium. And then we'll make half an equivalent of hydrogen gas, that will bubble out of solution. All right, so this is a good nucleophile. Not a God nucleophile. All right, now that we've got a good nucleophile, we need a good electrophile. So I'm just going to redraw this down here. And this electrophile could be any sort of alkyl halide or a tosylate, something like that. And this oxygen can hit that electrophile, do an SN2 reaction. And by doing that, we can now alkylate the oxygen with this R group, and we can make our new ether. One thing you do have to watch out for, though, is the nature of this R group, right? This R group must be a primary group or a methyl group. What happens if it's secondary or tertiary? Oh, it would do a reaction. It just wouldn't do substitution. What sort of reaction would it do if we had a tertiary carbon there? Elimination. We get E2 reactivity, right? So because this is a good nucleophile and good base, we have to watch out for that E2 chemistry, meaning that this R group must be primary or a methyl group. All right, so that's the more common way that you'll see ethers made. This is a lot more versatile than that industrial prep that I showed you before. Does that make sense? All right, sorry, I know we need better seating in this room. All right, we've also seen other ways of making ethers, although they were kind of thrown into the alcohol chapter a bit. So I wanted to go back to one of the reactions we covered in our alcohol chapter. Oops, shoot, I'm skipping ahead. And this goes back to alkoxymercuration. I can't say that very fast. All right, so let's think back to our chapter on addition chemistry. We said if you have an alkene, one thing you can do, let me actually spread this out more, is you can install an alcohol onto the more substituted carbon. And you could do this in this situation using just catalytic acid and water, or if you need to avoid rearrangement chemistry, you treat this with mercuric acetate, so HgOAc2, followed by H2O. The water in this case was our nucleophile that was added in. And then what did we need for step 2? Sodium borohydride. You can do the same thing, however, by switching out water with an alcohol, and if you do that, you can end up forming an ether. So for example, we could take the same starting material. We can treat it with mercuric acetate, but this time instead of using water, we'll use some sort of alcohol. It could be really any alcohol for this situation. And if we do this, we'll form our new ether where now we have an alcohol group. So this allows us to make a new ether functional group. Does that make sense? In fact, you can also use these same conditions to make a wide variety of functional groups. However, these are two of the main ones. Really, any nucleophile that's weak can be used in that step. So instead of an alcohol, you could use a thiol if you want. It would do similar reactivity, and you can make a sulfide that way. All right, so now let's take a look at the Actually, we only have 2 minutes. I think that's where we'll call it today. We'll look at the reactions of ethers tomorrow. For your problem of the day, I want you to review naming in your textbook or watching a video, and then answer the IUPAC names for the ethers given.